In this video, I'm going to discuss work done by a variable force. And I'm also going to talk a little bit more about work done by a gravitational force and work done by dissipative or forces or friction. When we defined work in class, I said the work is equal to the force acting on an object divided into the displacement. But this definition is only true if the force is a constant force. The more general definition is one that assumes that the force could be changing with the displacement. And if that's the case, then we have to define the work as the integral of, say, the force in the x direction over the displacement dx from some initial position, x initial, to x final. And I'd like to consider now where that's absolutely, this formulation of work is absolutely required for the case of work done by a spring. In this figure, we show an object that's attached to a spring, and the spring has been compressed a delta S initial from the equilibrium position. And then at some later time, the spring has become uncompressed and actually stretched and is pulling on the object, at which time there's a stretching distance, delta S final. And we'd like to know how much work was done by the spring during the displacement from S initial to S final. So we'd like to determine the integral of the force over ds from S initial to S final. And we know from Hooke's law that that force is equal to minus k times delta S, which we can write as the integral from S initial to S final of minus k times S minus S equilibrium ds. Well, this is a rather complicated integral, particularly if you're new to integrals. Many of you have had calculus previously and have already studied integration, but some of you are taking calculus at the present time for the first time. And so, and I know if that's the case, that you have not gotten to the part where you actually do integrations. So, in my demonstration of how to perform the integral, I'm going to do it for you folks in particular, using the method of taking the area under the curve to evaluate the integral. So the first thing we're going to do is we're going to replace this variable s minus sq with the variable u. And then we're going to rewrite our definition of work as minus the integral from u initial to u final of k u du. And while I'm at it, I'm going to go ahead and take that constant k outside the integral. So that's minus k times the integral u initial to u final u du. Now, for those of you who've already had calculus, you know that the integral of u du is trivial. It's equal to u squared over 2. And then you simply evaluate that between the initial value and the final value of u. But this is for the students who are taking calculus for the first time. I'm going to evaluate the integral u du between these limits using the area under the curve, under the u versus u curve. So let me draw that. Let's say that u initial is here, and 3 blocks later, u final is here. Then if that's true, here, let me move this. So I went ahead and completed my drawing of my u versus u graph. And recall that what we want to do is perform the integration of u as a function of u, du. And in order to do it, we need to find the area underneath this straight line here. So that area underneath this curve is the area of this rectangle plus the area of this triangle. So the area we want is the area of the triangle, which is 1/2 times the base, which is u final minus u initial, times the height, which is once again u final minus u initial. So the area of the triangle is equal to 1/2 times u final minus u initial squared. So that takes care of the area of the triangle. Now we need to find the area of the rectangle. Well, that's just simply the height of the rectangle, which is u initial, times the width, which is u final minus u initial. Then we multiply this all out. And when we do, we get the result that you see on this line. And we carefully do the math here. We see that this reduces to 1/2 u final squared minus u initial squared. Okay, so now we can write down our work for the spring as equal to minus K times 1/2 UF squared minus U initial squared. And I can rewrite this as minus 1/2 K U final squared minus 1/2 K U initial squared. Which we can rewrite as minus 1/2 K times delta S final squared minus 1/2 K delta S initial squared, which is the result that they show in the book. And it's written this way because later on in chapter 10, you will learn that this first term will be called the final potential energy of the spring, and the second term will be called the initial potential energy of the spring. But we'll save that for chapter 10. So now I'd like to say a little more about work done by gravity. And I want to revisit the example we did in class where we talked about me raising barbells from a certain height to a greater height. And here I show the system, and contained in the system are the barbells. And not shown in the system is the gravitational force, because in this example, the gravitational force is acting as an external force on the system and actually doing negative work. As the barbells are raised. And at the same time, I'm doing positive work. Work done by me as the barbells are raised. So the work done by gravity is equal to minus mg times y final minus y initial. It's a constant, so I didn't have to do an integration, a constant force throughout. Whereas the work that I did is positive work, and it's complicated because I varied the force. I had to give it a force slightly greater than the gravitational force to give it an initial acceleration to get it moving. But then once I got it moving, it moved at a fairly constant rate. And so the force I applied most of the way up was equal to the gravitational force. But then I decreased the force I applied as it slowed to the final position. So it's a complicated force over the displacement, and I have to write that in order to evaluate the work that I did, I have to integrate it from the initial position to the final position of whatever that force, however that force varied over the displacement in y. The result of this is that the total work done on the barbells is equal to the work done by me plus the work done by gravity. If there had been no gravity, then I would definitely increase the kinetic energy of the system. But because the work done by gravity over the whole displacement is equal to the work I did over that displacement, then they sum to zero, which meant that the change in the kinetic energy is zero. I hope that is more clear. Okay, then there's one other topic I want to discuss, and that's work done by a friction force. So say we have an object, say we have a block, and we're moving the block to the right, towards positive x. And I'm applying a pulling force, F sub A, and resisting this pulling force is a friction force, F sub K. So, as shown then, I'm an external force acting on the system, on the block. So let's draw our system here. And in it is a block. Okay? And together, I'm doing work tending to increase the kinetic energy, so the work done by the applied force is increasing the kinetic energy, whereas the work done by the friction is tended to decrease the kinetic energy, so that we can calculate the work. If I'm applying a constant force, work total is equal to the work done by the applied force plus the work done by the friction force, which is equal to F sub A minus F sub K F friction, F sub K, that's correct, times the displacement, delta X. Okay. Well, that's one way we can treat the problem. And when we do that work done by F sub A minus F sub K results in a change in the kinetic energy of our system. K is changed. An alternative way to do this kind of problem is to assume that the sliding surfaces are part of the system, so that the work done by the friction is internal to the system, and as a result increases the thermal energy of the system. So, in other words, we will redefine our system to include the block plus the friction internal to the system, so that we will change both the kinetic energy and the thermal energy, which I'll call ETH. So if that's the case, then the work done on the system is done only by the external force, S of A, delta X. And that's equal to the change in the kinetic energy plus F sub K, a quantity equal to F sub K delta X. And we're going to call this second term the change in the thermal energy. So that the only work done external to the system is that by the applied force, resulting in an increase in the kinetic energy of the block plus the thermal energy of the system.